So the computation of this estimate is not quite difficult, but the notation is messy. Let me see. So this value is of course either 1 or 0, and it will be 1 if and only if, so for all I, this element, this is in your two ideals. In other words, this is equivalent to, you have a linear map from here to here, so that was psi I, and you have the quotient map into the residue ring or residue abelian group, and you can multiply W and slide it to an element. So and it is certainly factors through some finite residue here, quotient here. The norm. So if and only if x goes to 0 after all the composition. So this sounds a little more understandable. So let's define an integer which we wrote d in our paper, depending on the tuple of ideals, to be, so d is the generator of the following ideal. For example, so let's take the product here. So product. So this is my definition. So then I draw an almost same diagram here. So I divide by d. So the previous condition can be stated as your function takes value 1 if and only if this linear map carries your element to 0. So now we have a bound of the size of d. So now, so this guy, this is at most the product of norms. Maybe because the product of ideals is the intersection of ideals is containing the product of ideals, and we can take the norm here. If you take the norm, you have an equality in the other direction. And we know that the ideals contributing the sum, your ideal can contribute to the sum only when it has norm at the most r. So these are smaller than r squared. So therefore d is at most r to the power of 2m. Now r, this box on which we are considering the average, so this is the box. So they have lengths at least 4 to r to the power of 4m plus 1. From this argument, it follows that the function, or this characteristic function, is dzt periodic, meaning that if you slide your original element by any element inside d to the d, then you get the same value. So this function has a period, but the period is very small. So like this has d, length d, and this is smaller than 2m. So much smaller than the entire square. So it follows that the average on the box is up to small error. I mean, to begin with, this shows that your function, this function, is well defined on the quotient, and your average is almost the same as the average on a fundamental cube. Yeah, so now let's compute this last quantity further. Computation of and let me slightly change the notation here. So I will write ideals by I, German A, not German B, because it might be easier to see, easier to read. For each tuple of ideals. So I used to write B, German B, script B for ideals, but now I change. I write A for ideals, the German A. So now we are considering this kind of map. So first I want to decompose the problem into P parts for prime numbers P. So I'm using I for A for ideals partly because letter B is already used to denote an element. So now for a prime number P, let's define the P part of an ideal to be, so I mean if A is written as the product of, so this is supposed to be German P, then its P part is defined to be a partial product of these guys, where this prime P is German P is over P, so it's equivalent to say this prime ideal contains the integer P. So the P part and we know some elementary properties for the P part. Namely, for example, if I take the intersection of two ideals and take P part, then it's the same as taking the P parts of each and take the intersection. Also, yeah, also let's denote, if let me see, if Z is an abelian group, so if Z is an abelian group, then you can agree what this P part means. So one way to define it is the elements small z inside big Z such that so let me so let's see, a finite abelian group, or maybe torsion abelian group. So it's and then these two notions of the P parts are compatible in the sense that we take the quotient ring and take the P part as an abelian group. Then it's the same as you take the P part of the ideal and then take the quotient ring or group. And now we consider, so by the Chinese remainder theorem, so the map I'm considering decomposes into the P parts and therefore the average I was considering this vector, sorry, 1 to m is 0 in, so this is the original average I was interested in without P part. Yes, this is an equivalent way of writing the average. This turns out to, I mean, this event happens only when, if and only if the same thing is true for each P part by this decomposition. Therefore, I can write it as, let me see, the product over P, it's a finite product. And I consider the same event, except that I take the P part. So this vector should be 0 in so we are reduced to the computation of each P part. Now